Okay, welcome to this website 2022 tutorial on Coornet and how to use this R package to detect problematic online coordinated link sharing behavior on online data. My name is Luca Rossi, and I'm co-presenting this with Fabio Giglietto from the University of Urbino, but the team behind Coornet is much larger, and the team behind today's tutorial also includes Nicola Righetti from the University of Vienna and Giada Marino from the University of Sussex. Today we will follow first a short introduction to the concept of online coordinated behavior, and then we will show the main functionalities that we have implemented in Coornet and how it can be used to support this type of research. You should now be able to see my RStudio interface. We prepared a little markdown tutorial for this event, and we will share it on the Coornet website so you can follow along with the code and with all the examples and the text and the references and everything else. So the idea of coordinated behavior online is a concept that has been around for quite some time, I would say, and it is based on the idea that in order to achieve a higher level of visibility on many social media platforms, users might try to pretend that the content that they are sharing is perceived as highly relevant from the user. And a way to trick the social media algorithms into believing that the content is highly relevant is to provide a large amount of sharing within a short period of time, because that is usually how it is perceived as something being of interest, of being hot, of being trending. So a lot of strategies have evolved around how to perform this kind of automated activity, and they both require automated type of sharing, like through bots or other type of non-human actors, but also through automated or semi-automated activity that involves coordinated activity among many users. And that's mainly the case of activism, where they try to put trend on the trending things, on the trending topic links, so they become more visible. So in order to do this, in order to perform the coordinated activity, as we said, we need to share a large number of content, basically the same link or image or text or whatever you want to share, within a short period of time. Thus, the key element here in order to detect this kind of activity are those two elements, the content and the period of time. So Coornet is an R package that we have developed to try to understand and to detect this type of behavior, working on a subset of this type of behavior, that is link sharing on Facebook. So when we are talking about content being shared in the context of Coornet, we mainly talk about links being shared, and the default platform where we are observing this sharing activity is Facebook. So Coornet, because of this and because of the background of Coornet works with CrowdTangle. It's basically a package that, in order to collect Facebook data, relies on the CrowdTangle API. So if you want to use Coornet, you need also to have a CrowdTangle API, and that CrowdTangle API should be stored in your environment, so Coornet can use it whenever it needs. So basically, what we need is a starting point. As a starting point is essentially a list of links with a timestamp. And those are the links that Coornet will go and try to collect through CrowdTangle all the shares that have been made on Facebook for those links. So our starting point is usually a file that is organized and is based on 2 columns, if you want. One column that contain the URL and one column that contains the date when we want to query this URL for. And the output of this operation is basically a longer file containing all the shares that those links have received on CrowdTangle. This first part of activity is what is achieved by the function getCityShare. I'm gonna zoom in a little bit here, so maybe it's easier to read. It should be relatively large here. So the first function that we are introducing here is this getCityShare, and getCityShare is the function that, starting from a data frame that contains at least 2 columns, one where we have the URL that we want to query and one where we have the date relevant for those URL, and this function will query CrowdTangle for all the links, all the sharing activity performed on those links on the specific platform. CrowdTangle also deals with like Instagram and other platforms, so you have the possibility to specify, for example, Instagram here, but this type of activity is not like hugely popular on Instagram, so we're going to work with Facebook data. So this getCityShare basically takes here the object, here the column containing the URL, and here the column containing the date. And this is the function that requires you to have the CrowdTangle API key. So if you don't have an API access to CrowdTangle, you cannot use this function. This is the key part of the whole process in a way. This, because of the limitation of the ratio that you have to access the API and maybe to the number of calls that you need to make, this can take quite some time. But the function is written in such a way so that if you run out of attempts, it will just pause, wait a little bit, and try again. So it takes time, but eventually you should end up with a document, an object that will look like this one. I don't know, Fabio, do you want to describe this document? Might be useful.
Yeah, basically this is the standard output of the CrowdTangle API when you query for posts. And in this case, we are querying for posts which share a certain kind of links. So basically you get quite a long list of fields which describes the post and the interactions gathered by the post during basically its lifetime until we queried this data. What we actually do on this data sets is to extract the URL from the post itself. And we also check if during the process of the function CityShare, if the link which was shared by the post was contained in our starting list of links. And that is it's something which we may want to pay attention to while we are getting posts which does not include links from which we started from. And this is because of the way Facebook works. Each post can carry multiple links. So when you query for a certain link, you get back a list of a data set which has multiple rows depending on the number of links posted through the post itself. And then I will pass to Luca again.
So anyway, it's interesting here that the first output that we get from this city shares. First of all, we need to keep in mind that this is not coordinated sharing. This is all sorts of sharing. So the first step that Coornet does, and this workflow assumes, is to get all the shares, and then we will see in a second how to identify the coordinated behavior. But the output of the get city share basically contains a lot of information that, in a sense, can already be used and analyzed, because you have all the shares of the links, the expanded information of the link, you have information about the accounts that have shared the link, for example, the type of account, the account of the subscriber to that account, the handle, the date when the account was created, but also you have information about how the Facebook audience or the other users reacted to the link when it was shared, because we have accounts for all the emotional reactions like love, sad face, etc., as well as a bunch of other information. So in a way, this in itself is a useful data frame that contains a lot of information related to the initial set of links that we started with. And as you see now, we are working with something in the order of like 44,000 rows that is basically sharing actions. Now, as we said, all these shares are not necessarily coordinated activity. So what we need to do is to identify out of those shares those that we suspect being coordinated. Of course, we have no way to know for sure that a certain type of co-sharing is coordinated. I mean, we have no way to peek into user's mind or to understand exactly what type of actor was behind the sharing. But we have a way to suspect that a certain type of sharing might be coordinated. And usually in the literature, this is done through identifying a short period of time, like a very short time interval, under which we decide, well, this sharing activity is too close to be natural, or is too close, thus it must be, it is suspected to be coordinated. That can clearly be done in many different ways. And it can be done setting an arbitrary threshold, saying everything, all the shares that happen within 1 second must be counted as coordinated, because it's unlikely that we're all going to share the same link within 1 second. Or it can be done in a different way. Let's call it like a statistically informed way, and that is the option that Coornet adopts. There are pros and cons of going with this strategy. Let's first see the function that does this estimation of the coordination interval. So the function is this estimate coordination interval, and it takes as parameters, it takes the crowd share, the CrowdTangle object we just produced. This we call it the FCT, and then it takes other parameters. Let's first run it. Maybe if I load Coornet, might be a good idea. As you will see, this is also can take a little bit of time. Fabio, I don't know if you want to explain the parameters in the function.
Yeah, actually, I have to say, I personally never use this kind of parameters, but basically, the algorithm itself look into very unlikely short period of time between two shares, and you can tweak this. What we mean by unlike by setting this Q and P parameters, which is, well, basically change a little bit the way you estimate the coordination interval. The interesting thing is here that, as Luca was pointing out before, there is no magic number here, and sometimes it really depends on the data that you are working on. And sometimes you can end up by choosing an arbitrary number based on the literature where these kind of studies are flourishing, and we start to see some convergence on what it is considered to be a good approximation of an unlikely short period of time.
So one thing we should always remember is that when, as we will see later, we can decide to have like an arbitrary way to set the coordination interval. Thus, you pick a value, taking that value from the literature, or we can let Coornet estimate the coordination interval or through this function. In this way, we can see the output, and we have basically the summary of all the coordination of all the time intervals that we see between sharing. Basically, the smallest time share is 0. That means basically is sharing at the same time. Then we have the quantile, then we have the median value, and then we have the maximum observed distance between two shares. Using this information and using this quantile parameter here, the estimate comes down to 9 seconds, and that is what Coornet identifies as our threshold. What we need to be aware of is that Coornet will always produce a coordination interval. There will always be a result here, no matter how unlikely is that that number might actually represent a coordinated activity. If you input a data set of sharings where there is absolutely no coordinated activity, and there is actually a lot of time between the sharing activity, you might end up with like a suggested coordination interval that is, I don't know, like 20 seconds, 1 minute, 200 minutes. It doesn't matter, right? There will always be a result there. So it's a good idea before using this, like just out of the box, to check if the suggested coordinated activity, suggested interval for coordinated activity that Coornet identifies is actually reasonable. And we can say, well, 9 seconds seems short enough to be a good number, right? Once we have this, and we have basically covered the first part of our definition of coordinated behavior. So in a way, what we want to do, and what is actually the goal of Coornet, is not only to identify coordinated behavior, like to identify the shares that we can count as coordinated, but it is also to identify networks of actors that have performed this type of activity. So if you think about it, now we need two different types of information. One is an information that is time sensitive, basically our coordination interval, how close to sharing activities need to be in order to be counted as coordinated. But we also need to add another information. And the information is how frequently this coordinated activity need to take place, need to happen, so that we can connect to actors and say that they perform coordinated sharing together. Of course, we could put this threshold down to like 1. So as long as 2 entities have shared something within our coordination interval, we will count them connected. But experience and like observation shows that it's very easy for Facebook entities to share things within a very short period of time. And then if we only use this coordination interval as our only parameter, basically we will end up connecting everybody with everybody, all the entities with all the entities, and that will give us very little information. So what we want to do is to set another threshold saying, well, it's not enough that you share something within the coordination interval once. We want you to share something within the coordination interval with the same actor several times. So basically, we need to identify another threshold. And this threshold is identified in the second function, that is this get coordinated shares. Basically, what the get coordinated shares does is basically a function that collects you all starts from the shares that we have identified and uses the information, the time interval from the that we have estimated here. So in this case, we set it manually to 10 seconds because we saw it was 9 seconds here. But if we don't specify this parameter, basically Coornet will just run this function and use this output. And this is why it's important to be aware of what that number might be, because if you don't specify the coordination interval here, Coornet will just run the function, take whatever coordination interval is suggested, and go with that. So you might end up having a network with a very unrealistic coordination interval. And then there is this percentile H weight. Basically, this is what defines the frequency of co-sharing, of coordinated co-sharing that two actors need to have in order to be counted as actually connected. So basically, this is how it works. Using the coordination interval, Coornet goes through all our sharing and identifies all of the sharing, only the sharings that are coordinated. Then it builds a network with all the actors that have actually performed coordinated activities. And then using the distribution of how many co-sharing activity there is between all the actors, it identifies, like in this case, a quantile and it removes everything that is below that threshold. Of course, this could be put to, I don't know, 99 if you want only to keep only actors that really have performed way more connected coordination, connected coordinated sharing than the rest of the network. So basically, the
Luca,
higher, yes.
Can I add something, if
Sure.
you don't mind? Yes, Luca basically perfectly explained the logic behind this operation. But since you are choosing a quantile to filter the network in terms of the number of coordinated shares performed, basically at a certain point you may want to know which kind of number of coordinated shares you filtered for. And for these reasons, Coornet creates a log file in its main directory, I don't know if you want to have to open it in from the main directory. There is a log.txt file.
Yeah, sure.
And as you can see in this, you will see in a moment that as soon as we run the function, we will get some new information here, which will let us know what does it mean to filter for 0.99
Now
percentile edge weight.
I need to load the data. Just a second.
And it is interesting to the fact that basically the detection of coordination that we employed here is based on two-step process. The first one is using the coordination interval to basically identify potentially coordinated activity. But if you think about it, it is perfectly fine to, and it may happen that two separate Facebook accounts share the same link at the same time. Maybe me and Luca, we discovered a new interesting link, and we decided to share it. And by chance, we shared it at the same time or about the same time. But that does not mean for itself that that me and Luca we are a coordinated network. But if me and Luca repeatedly share the same link at about the same time, then you can see how these things becomes definitely more suspicious and may be considered coordinated. And you see that the process of identified coordinated shares just started. I don't know, Luca, if you want to
can take a little bit of time. So it depends on the size of the data set you're using. It also depends on your machine to some extent. There are options to speed up the process, like you have this parallel that uses some capabilities of parallelization. It speeds it up a little bit, not enormously, but a little bit. And there are also other options and other parameters that we are not describing here, but the package in itself is quite well documented, so you can just read through the PDF to have a good understanding of everything. So now, while
sorry, go ahead. No, let me add something about the performance and the kind of machine you may need to perform coordinated detection with Coornet. Basically, it really depends on the number of links you start from. Because of course the number of links will determine the number of shares obtained by these links, and it is quite easy to get back from CrowdTangle a large data sets of shares, basically. Which means that sometimes, even because we all know that R is not exactly the best tool in terms of RAM management, that you end up basically stacking. If you look at the the amount of RAM that we are just using, you get an idea of how it can scale dramatically. And to tell you the truth, often I had to run very large machines in terms of RAM, and in order to do so, we tend to use cloud-based computing. There is actually another reason which is very practical to strongly suggest you to go for the cloud-based option. It is the fact that when you collect the shares, it really can take a lot of time, because it means basically that you are querying the CrowdTangle API multiple times, depending on the number of URLs you are starting from, which means that it will take time, because we also know that there is a limit in terms of the number of requests we can do to the CrowdTangle API. So what it practically means is that your computer must be connected to the internet for the whole process. And if something goes wrong, your computer goes in standby or your connection drop, you basically have to start over from zero. So if you instead use a server which is permanently connected to the internet, then of course you can avoid to rely on the connection and on your computer itself to get the information you want. In the meantime, the process is about to be completed. You see that there are two phases. The last phase is actually build and filter the graph, and Luca will explain it in a moment.
Yeah. So basically, as we said, so this phase, this get code shares, is actually does a little bit more than just getting the shares that we consider to be coordinated based on the coordination interval. What it does is that, yes, it goes through all the shares and it identifies the shares that are according to that coordination interval coordinated. Then it uses those shares to identify, to build a network of actors, and then it filters that network of actors based on this percentile edge weight. Now we can see if the log now shows some additional information. So we have the get coordination script when it was executed, the coordination interval that was used, the number of links that were shared in a coordinated way. Basically, that is basically 21% of our initial data set, the number of links that were shared in a non-coordinated way, the percentage weight that we set, and that basically corresponds to 3 times to having shared links in a coordinated way at least 3 times, and that basically will result in having 192 actors, entities, as we will call them, in our network, that will be organized in 55 components. We will go into the network side of this in a second. But basically, the log file here gives you a lot of useful information that then you can use later, or that you should probably use later when you're writing about this, because these are all the details that basically created the data that you're gonna observe. So let's see what is the output of this function, because now the output, as you can see, is no longer a data frame. So far we've only worked with data frame, but now we have a list of three objects, of 3 elements. So this contains, let's explore it a little bit. This first contains basically the same data frame we had before, with all the information. So the platform ID, the platform, the data, the type, the title, the description, all the columns we had before. But now you can see that we have an additional column that says is coordinated. and this is coordinated column. Sure. Will contain a logical value true or false, true if the specific shares happen to be within the coordination interval, and false if otherwise. Then the second element within our list is an iGraph object. iGraph is a package to handle network data and graph objects. So this is a network, basically, and we will describe this in a second. But this network contains is a network representing all the entities that have performed coordinated link sharing at least a number of times equal or higher the number of times that we have seen in the log. In this case, that have been co-sharing the same link within the coordination interval at least 3 times. And then the third object is basically another data frame that contains a lot of information about all the entities that have performed this type of activity. It contains the names, the number of shares, the number of coordinated shares, the average number of subscribers, and so on and so forth. We will describe all these 3 objects in a second. So basically, what is important to understand is that now we have moved from one data frame containing all the shares of a set of links performed on CrowdTangle, on Facebook, to 3 objects containing slightly different information about the coordinated behavior. So we're gonna work with these 3 objects one by one. So the first thing is to explore the actual coordinated sharing activity that we have observed. So we're going to basically show a bunch of plots to explain the type of information that we have here. But from now on, one could say the package, the key functionalities of Coornet are almost over. There will be some utility functions that we have implemented, but at this stage, we have already queried CrowdTangle. We have already statistically identified a coordination interval, and we have already applied those information to create a network of coordinated entity and to create a data frame of marked coordinated sharing. So the first thing we can do is, for example, now that we have a data frame telling us, so yes, this sharing was performed in a coordinated way and this sharing was not performed in a coordinated way, we can, for example, see, okay, let's see how many shares were coordinated, is something we already saw from the log file, and if those were performed by, I don't know, like Facebook groups, Facebook page, Facebook profile, or some other entities. So we can just look at this and see, well, in our data set, coordinated activity is present, but is not dominant, which is almost always the case, right? Out of all the sharing that exists on Facebook, it would be strange if you only get coordinated sharing. But we can also see the link type corresponding to the different types of sharing activity, because as Fabio was saying, Facebook works in a very complex way. So basically, a link can be shared through a different type of post within Facebook, and we can see that in many cases in this data set that we are using with, we have corresponding like link type of links, but also types of photos, YouTube video, native video, live video, videos, and status. Right? So we have multiple types of Facebook objects that were shared that contained the initial link that we were working with. And of course, now that we have all the shares, we can say, okay, let's see this URL that were shared overall, you know, what reached the highest level of a certain metric, because now we have all the links, and with all the links we have all the corresponding shares of that link. So we can basically say, well, this link, if we take all the shares into account, corresponds to, I don't know, this very high level of engagement, or very high level of emotional reaction, or very high level of some other metrics that you can imagine. And this, in order to do this, we can use this utility function that we have created, that basically is this get top coordinated URLs, and basically here takes the links that were shared in a coordinated way, and it provides a way of ranking them according to a specific metric of your choice, right? This is based on the statistics that we have available through the CrowdTangle data. So basically you can rank according to engagement, which is the default. If you don't specify that, we'll rank according to engagement, or you can rank according to the like, you can rank according to the share, the comments, love, wow, and everything else. So here the results is basically a data frame containing the object, the link, containing the number of shares, the level of engagement, and all the statistics. It's reasonably simple, but it's useful because you might want to know, okay, in terms of engagement, this Washington Times news reached a very high level of engagement, even compared with the others. So maybe it's something worth, you know, even if it was shared not the same number of times, it reached a way higher level of engagement. This is a useful function, because what we can do at this stage is to go a little bit more in detail and study maybe specific links that were shared. For example, maybe we might decide, oh, this link here might be interesting. It might be an interesting story that reached maybe a larger crowd than we expected, or a larger crowd than the other links in our data set. So another utility function that we have implemented is a way to visualize this this propagation activity. Now I'm using.
Basically, this function is based on something which CrowdTangle described as historical field, which basically includes all the information about, here we go, about the you saw before that for each post we got the number of interaction, the volume of interaction for each metric, but that is observed at the moment where you run the query. The historical function allows you to go back in time, and you get basically how many shares and interaction each URL got every about 15 minutes, or each time CrowdTangle basically collect this data for us.
So yeah, there might be some warning there to fix in the function, but basically this is the idea. This is very large data containing a lot of interactions. So this is an interactive plot where basically you can say zoom in and maybe zoom in again, because this is very rich, and you can see at each stage, at each kind of share, you have an information about the actual page sharing, and the page that were the actual shares were identified as being coordinated are marked as in red. For example, now with one coordinated sharing there, and that is very close to other shares that are not considered coordinated. And in this way, you can see how the link basically accumulates share. Now we can reset the whole thing, and you can see that, for example, there are two, maybe three main moment in time of coordinated activity around this this specific link. And what is this? Why is this interesting? Is because a lot of the activity that we observe is never just coordinated or non-coordinated, but we can see that coordinated activity can be used in many ways throughout the lifetime of a link. If you want to imagine like a link as something that is born and it grows as long as it gets shared, right? And we can see that coordinated activity can be used at the very beginning, maybe to boost up or kind of to bootstrap the link visibility, or it can be used while the link is already growing organically, just to spice it up a little bit, or to revive a link that was kind of like going to die off, or something like that, right? So in this way, we can study each link, how and when and by which type of actors they have been shared in a coordinated way. So the first part that we have focused on is this basically first object that was produced by our getCoordShare function, and is the list of all the links that were shared in a coordinated way. The second object is the network object. And as a reminder, the network object is a network created by all the entities, the Facebook entities. And by Facebook entities, this is something we haven't said before, but because this is based on CrowdTangle data, we are only observing the sharing activity performed by verified public profiles, Facebook groups larger than 100,000, Fabio, am I correct?
Well, it's the coverage of CrowdTangle is quite complicated, but they say they track popular pages.
Popular pages and large public groups. So this is the network, and so these entities must to be connected in a network. These entities must have shared the same link within our coordination interval, at least in our case 3 or more times. But this number of co-sharing activity is defined by this parameter that we saw before. So this is the network. If you are familiar with iGraph, you should be able to read this information. But basically, is a very rich network, because we try to attach to the network object as much information as possible to make it easy to use and interesting. So basically, we have, of course, the name of the entities. We have a lot of all the information we have about the entities. Platform ID, if the account was verified, if they have the top country, if it's a page, the type of actor, the account page category. So all this information basically are taken from the CrowdTangle output and attached to the network. Then, before creating the object, we also enrich it with some network-specific information. For example, the degree of the network. We identify the components and we attach a number for each component. We'll discuss the component in a second. We perform some community detection and we attach an ID for each community. We calculate the strength, that basically is the overall age weight that the node has with the surrounding nodes, and the weight on the edges. This weight on the edge is basically the number of times that those two entities have performed coordinated link sharing. So basically, this is an attribute for the edge, but in a way it translates to these strength attributes, because this is basically the sum of all this weight for the single node. Now we can see few information about this node. For example, as we saw also from the log file, in the network we have 192 nodes that are connected through 378 connections, and this is organized in 58 components. So this is something quite specific of studying this type of network. I'm gonna first to try to visualize the network, okay, and then we can discuss. Let's visualize it. So it will appear here, and it will be easier for us to discuss. So, so when we do network analysis, usually it's not uncommon, actually it's quite common to work with multiple components, but usually there is this idea of, well, there's a giant component, that is the component that basically represents the bulk of the phenomenon that we are studying, and we can almost safely focus on that and work on that, because we have a nice, well-connected single component, and then we ignore or discharge everything else, because usually have a small component of little interest, because what we are interested in usually takes place in the giant component. And it's no secret that a lot of metrics and analysis that we commonly do in network analysis are designed to be applied to the giant component or to a single component, and it's harder to read or compare those when we start working with multiple disconnected components. But when we observe and when we study this type of online behavior, we almost never have like a single giant component with like smaller components that we can safely ignore. We might end up in a situation where we have a giant component, but it's hard to say that the smaller components are of no interest and that we can safely ignore them. And this is a very interesting case because here we see that we have multiple components, 55, and it's hard to identify one component that is more interesting than the others. You can see those are all extremely dense internally, like they are almost all white clicks. We could verify that, but it's hard to say that this, for the sake of this analysis, this is going to be more interesting than this one, or this is going to be more interesting than this one. So what we need to understand is that when we do network analysis in this kind of context, it's more a network analysis aimed at understanding the components and how they are isolated and what is the difference between the various components, rather than identifying like the major component and maybe performing some, I don't know, community detection on top of that. Another interesting thing that we can easily observe here is that the activity that takes place in groups is dominant compared to the activity that takes place around pages. And we can often see this distinction of components that are based just on pages and components that are based just on groups. Now, groups and pages are extremely different type of entities in Facebook, and they're used in a very, very, very different ways. So it's interesting to observe this also here. Now we can, of course, because we have all this information stored in an iGraph object, we can simply perform some analysis, and for example, we can group we can identify the clusters, so we can identify the pages of the groups, so we can arrange them in various ways. There is some coding here that extracts the name of the account, the type of the account, the degree, the component, the cluster, and these are arranged because according to the number of clusters. The number of clusters is just a number. There's no real interest here. But what we can do, and that is probably more interesting, is to see. For example, the degree of our nodes, right? So, if, for example, the degree distribution is something that we usually observe in networks, but again, keep in mind it's slightly different when we study the degree distribution of a, let's call it, social network or a normal network, to when we observe the degree distribution of this type of network, right? Because we have several components that are basically cliques, fully connected. So basically the maximum degree of those nodes will be defined by the number of members that are in that cliques, and that basically creates our top down this here, right? And then we have a lot of other smaller components that are just dyads of two entities, and they create this part here. But we can see that, for example, also from our degree distribution, this network is quantitatively dominated by a lot of like 2 nodes, groups, and a few cliques, counting many more nodes. Of course, we can also see, and this is basically the same information, just visualized in a different way. We can organize our component according to the number of members they count. And as you can see here, we have like 2 components with this could be like almost 20 members, and then we go down to a bunch of components with like 8 members, and then we basically have a long tail of components with just 2 members. And this gives us an idea of propagating of coordinated activity taking place in several spaces at the same time throughout the Facebook space, rather than having just a single source of coordinated activity and everything that kind of like sprawls out from there, right? We don't have that kind of scenario. We don't have a single source of coordinated activity. And if you want to connect, as it's usually done, if you want to connect coordinated activity with like problematic information, you don't have a single source of problematic information, and you can simply take that out and you will fix the problem, because this is the picture we are dealing with a number of disconnected networks where coordinated behavior is largely used. Yeah. And then we have additional community utility function. And in the latest version of Coornet, we have introduced a very nice functionality that relies on NewsGuard APIs. So if you happen to have an API key for NewsGuard, you can save that into your R environment, and when you run this get component summary, you will have an additional information about the if you want the NewsGuard rating that measures the quality of the links that have been shared within the that specific component. For example, let's first see. So this is the output of this function get component summary, and you get, well, the ID of the component, you get the number of entities. You can probably visualize this. You get the ID of the component, the number of entities, the average of the subscriber of, this is the average of the subscribers of all the members of the component. So in a way, it's an indication of, okay, this is a component made of entities with a lot of subscribers, or is a component made of entities with not so many subscribers. We have a ratio of like how many coordinated activity there was. If these have an A here, because these are components made of groups, so they don't have an admin with a country. But if the component is made of pages, we have a country for the admin of the page. This is the number of pages in the component, the number of the groups in the component. And we also have the NewsGuard, this NewsGuard score for the links that have been shared in that component. How many links shared within that component have been rated by NewsGuard, because of course NewsGuard does not cover everything that exists online. So you might have a very low score or a very high score, but it is only one out of like, I don't know, like how many links might have been shared within that that class, that component. And then we have a Gini index that shows basically the diversity of the links shared within the component. Basically, if they all share the same URL or domain, basically you will have a very low Gini index. And
Luca,
and yep.
Let me add something about the NewsGuard score. If you can go back to the columns where the NewsGuard score is displayed, what you have to know about the NewsGuard score is that they use this rating that goes from 0 to 100, and from 60 to 100 they consider a news source reliable. It's a manual process done by journalists and so on. And as you can see here, we are getting very low average score of the domain, sometimes with a coverage of the network quite high. If you scroll one column right, I saw there was one of the component with 70% of the domain is the one with 8.7 and 12 domain rated. It has a coverage of 70% of the domain rated, so it means it's a quite good coverage, and they are getting 12 as an average score. So it's a hugely problematic. You can just
we can also see it here, right? Now I just ranked those according to the coverage of the domains, and these are all 100%. Of course, these are small numbers because basically these components only shared a few domains. So all the links they were sharing, they were all referring to the same small set of domain. But you have basically like at least those two. They have like 30 in the 30s. This is extremely low. Those are better quality. So you see it's an easy way to understand, especially with high coverages here. I would say above 50 somehow. It gives you a good indication of the journalistic quality or just journalistic reliability of the information that is shared in this class, in these components. And then of course then you can just go and you have a component ID, so that you can, for example, identify just can go and verify, okay, what are the actors or the entities within component 40, 47 or something like that. Okay, of course, just to remind, to stress this one more time, this is available, is a functionality that is available in the latest version of Coornet, but it requires with like a NewsGuard key for their API, and we do not provide that. You have to get it yourself. Of course, let's see what was the nice component we saw here. The one that was pretty bad. So let's see this one. Okay, number 47. Because once we have a component, we can clearly extract that component and have like a more detailed exploration of the component. And you see like this is a component, and it shows like it's a small component, just 3 groups, with like Conservative Party USA, Conservative Party Florida, and another Conservative Party. So it's a way to identify then the single component that might be worth of interest and exploit, right? Because we have a lot of things from different countries in this data. Let me see. And of course, if you want to, once you have an iGraph object, it's very easy. We leave the code in the there to save the graph or the subcomponent you might have exported as a graph file, and open it and explore it with the software you prefer. Like to make a visualization, you can use things like Gephi or other type of software that can make even like a nicer visualization to put on a paper or something like that. Now we move to the third part, to the third object that composes that is part of the output of the of our get code share function. So we saw the first, the data frame containing all the sharing activity with a mark if the sharing activity was coordinated or not coordinated. We saw the second object that was this graph with a lot of additional information about the type of actors, type of entities, and their coordinated behavior. And then the last part is specific about the entities. In a way, this data frame takes information out of the network and out of the initial sharing activity and put it in a more easy to explore type of way, right? So these are the information we provide here. There is the name of the entity, the number of shares, the number of coordinated shares, the average subscriber count, if they have their handle, their account name, all the information that somehow we have also seen before is now organized in a data frame that only contains information about the entities. And this allows us for additional exploration that has a slightly different focus, because the first focus was on the actual content being shared. The second focus was on the network emerging from that sharing activity. And the third focus is on the entities who perform the sharing activity, right? For example, we can see, we've seen this before, but now we see it in a slightly different way, that this type of coordinated activity in our data is dominated by groups. But we can also see, okay, let's try to make some plot where we have the average number of subscribers and the number of shares to see if there is a relation between how active they are and how many subscribers they have. Or and it's the same. We can just change this to something else. For example, number of coordinated shares. All right. Just to explore even more the data in this way. So this table actually does not introduce anything substantially new. I think the information you can get from this third object, from the entities table, is by large already available in the other two, in the shares and in the network, is just a convenient way to focus your analysis on the entities rather than focusing your analysis on the network or focusing on your analysis on the content. But conceptually, the organization of Coornet is that we start from the content being shared, we identify the content being shared in a coordinated way, and then you can evolve your research or focus your research towards the content, towards the entities, or towards the networks, group components in the network, the groups of connected entities that emerge from the content.
Yeah,
yeah.
Let me ask something about this. Basically, Coornet allow you to browse the data with different level of details, but also with slightly different level type of approach. Basically, if you you can use the graph and go through the graph and use basically network analysis to explore the relationship between these entities. Or maybe to map the relationship and to visualize the relationship in a visual way, which sometimes is very useful and enlightening. On the other hand, sometimes you need a table format to explore this data because it will be easier to, for example, export the table of coordinated accounts to a spreadsheet in order to run a content analysis on it, or to simply have a easier way to browse through this data. But most of the time, I have to see, based on my experience, you end up by combining the two approaches. Because visualizing this kind of data with a map through using social network analysis is extremely useful, and from there you can switch to the table view and combine the information in an effective way. That at least it's my experience. And also we saw that Coornet also provide a list of coordinated shares plus the coordinated non-coordinated field. That is, it is extremely useful if you want to go more in depth on the data. For example, you want to know something about a specific URL or a specific post shared by certain account. And it is useful because sometimes you want to see this post in their original context on Facebook to understand exactly how this this behavior of coordination took place on Facebook.
Yeah, and of course, the moment you start having all these different tables, you can always like rank the data and organize the data in different ways. For example, you can say, okay, let's see, because it's hard, especially in a situation where you have this many disconnected components, and you really should read this as activity that takes place in a almost independent way throughout the network in various places. You might want to say, okay, maybe we want to rank this in terms of their effectiveness rather than ranking them in terms of the number of connections. And maybe then you're going to rank those in terms of, I don't know, subscribers, or in terms of engagement they reach through their activity, or in terms of the kind of content you're going to share. So the strength, I think, of the data produced by Coornet is that it allows you to slice the data in many different ways. So you can opt for many different research strategies. For example, you can identify, look, now I'm looking at this entity table, and we can see that we have different type of groups of pages from different parts of the world. You can simply see that also from the language they use, right? So this also gives you somehow the international dimension of the coordinated behavior we are observing here. Yeah, and this is basically more or less what we had to share about Coornet. The package. Yep.
But yes. Shall we close with some links and references, basically to the Coornet and.
Yep. So the let me just okay. The package is available on the website. It's coornet.org. I'm sharing my browser, right? No,
actually, no.
I'm still sharing. Okay. Just let me. Okay. Is available here, and here we're gonna put all the information and all the new version and all the updates. We keep creating a new tutorial with different cases and with different examples. For example, we have an example working with media cloud data as an input for Coornet. We have examples working with CloudTangle data as the input source for Coornet. But just to remind you, as long as you have a list of links and a timestamp, that's all Coornet needs to start querying CloudTangle for shares on Facebook. So here we keep updating the version. Of course, on the GitHub, there is something more in a way, because we are currently developing new versions and we're currently improving Coornet. So some of the functionalities we have exported now in the current version. We were for today's tutorial, we were planning to keep them until a future version of Coornet will come out, but we decided just to share them anyway. So there are different branches, and you're very welcome to, go through the code, to check it, to suggest and to improve also on what we have done. We are in no way, we're fairly sure that there are many aspects that can probably be improved along the way, but so the code is available and you can just work with that. Yeah, I don't know, Fabio, if there is anything else you want to add.
No, I think that's it. And please get in touch if you are working with Coornet, and let us know if you need further help or if you. What?
Yeah, there are many things. Of course, now it's not totally clear what the future of CloudTangle will be. So if you don't have a CloudTangle API right now, it's kind of probably going to be hard to start working with Coornet. That at this stage relies on CloudTangle APIs. Meta is working on new APIs for researchers. If the functionalities that are available through the CloudTangle API will be made available to the new Facebook Research API, we will certainly move Coornet and release a new version of Coornet so that it can work with that. This stage, this is still uncertain, but Coornet is in active development. So as long as it is possible, we will try to make it happen. Yeah, and thank you for listening to this tutorial, and get in touch if you plan on working with Coornet.
Thank you. Bye bye.